Hello everybody. Instead of discussion this week, we're just going to do a video because discussion is on Thursday and that's Thanksgiving, and you better not be watching this instead of enjoying your break with your family. So hopefully you're watching this a few days after. But as you can see, this week we are doing Markov language model. And if you don't know what that means, that's understandable. So Markov, this is Mr. Markov. Look at his beard. So Markov basically came up with this model that's good for predicting different things. It's kind of like an AI predictor type of formula. And what it basically does is, in this case, what we're going to use it to do is we're going to use it to predict words, and we're going to use it to generate fake paragraphs and fake sentences and even fake essays. So if you're staying up late, writing essays for your writing classes, then this should solve your problem because you just run this program, it'll generate essays for you. So let's take a look at this. First of all, does this look real, like it was written by a human being, or does it look like it was generated by an AI program like the one we're going to write? So it is a little poetic, but it's definitely written by a human, right? So this looks too real. It's written by a person. It's got to be, right? Well, what about this one? So this is the first line or so makes sense to me, right? You read it and it's like, oh, that sounds like it's written by a person. Then it starts to get a little off, and you realize this is written by a robot. It's not real text, but it looks pretty good. It looks pretty close. And if we do that with something simpler, with fewer words in the book, right? Like green eggs and ham, which is like literally only like 50 different words, 50 unique words in the whole book, it gets really good. So this is generated by an AI, but it looks a lot like the real text. And that's actually what we're going to be doing this week. So I have green eggs and ham.txt right here, right? And I just run my program, and it actually generates a paragraph, and I can make it generate more. I can make it generate like a whole book, but it matches up with what it looks a lot like. It's really written by Dr. Seuss, but really this was just predicted using our program after it read in the real green eggs and ham. It made its own green eggs and ham, which is a little off, but it's really close. It did that using probability and statistics. For example, given some state we're in, we have a certain chance of moving to a different state, a certain chance of staying in the same state. So that's basically what Markov model is. And if that doesn't make sense, we'll look at how that applies to us. So if our state, we could say our state is like the last 3 words that we have predicted. And after predicting these 3 words, they are our state. And given this state, what will be the next word we predict? Well, if you're the AI and you read in green eggs and ham.txt, you know that if this is my state is green eggs and, then you should know that the word following the state should be ham, because you're a Markov language model and you're smart because you use probability, right? This is kind of a graph. If I read in green eggs and ham, green eggs and ham, green eggs and ham, and I'm a Markov language model, then I know that 3 times we had ham follow green eggs and 1 time we had bacon follow green eggs and. And what it's going to do is 3 out of 4 times, then it will predict ham if it's in the current state of green eggs and. And of course, 1 out of 4 times it'll just predict bacon. So there's the chance of predicting the next word is proportional to what words it read in, right? 3 times out of 4 it read in ham, so 3 times out of 4 it'll predict ham. Cool. And what we're also going to be using for this assignment is a hash map and word count list. So hopefully you can see why we'd be using word count list if we go back here, we can kind of see, well, ham is a word and it corresponds to a certain count. That count is 3. Then we have bacon as a word and that corresponds to the count, and that's 1. So hopefully that makes sense. If we have a word count list of 2 word counts, one is ham 3 and one is bacon 1, we can totally represent all of the words which should get predicted by these 3 words, green eggs and. Right? Let's go back to these 2 things later, but as you can see, this is our hash map. The key is an array list, and it maps to a word count list. So given an array list of words like green eggs and, we could map that to a word count list like ham 3, bacon 1. And they correspond. So given the prefix, we can always find the value. The prefix is the key here. Right? So for example, like I said, green eggs and maps to ham 3, bacon 1. And other prefixes like I do not or I will not or whatever map to other lists of words based on what those words will predict. So first of all, your word count list should be working. Hopefully you downloaded it from Gradescope or you still have it on your computer and everything like that. But besides that, what we're going to be doing is basically, if I read in after green eggs and I read in ham, then I will know that into my hash map I should have green eggs and corresponding to 1 ham. And then the second time I read it in, I already have this prefix in the hash map this time, and it corresponds to this word count list value. Then I will modify the word count list value to have 2, because I read it in a second time, and the third time. And then I read in bacon, and I modify the value to have bacon 1. And this is the same prefix still mapping to this object. Now one thing we got to be careful about, and I'm honestly just going to use Microsoft Paint to draw this. One thing we have to be careful about is, although we displayed it like this, what's really happening is box, line. What's really happening is this key, it isn't like this. It isn't green eggs and is inside like of the actual key. It's actually being pointed to because it's an array list and it's an object. Right, you get the idea. So it's a list. And likewise, this is pointing to word count list. I'm not going to draw that. You get the idea. Oh my god. So that means that just remember that not only your keys but your values, both of them are references to objects. So you can't just treat them like values that are stored inside of the hash map. The value inside of the hash map is just a reference. So be careful with your memory models. Always draw memory models out, and they should look like this when you're writing your code so that you know what's happening. Because a lot of people get confused, and then you get stuff like null pointer exceptions, or it just behaves incorrectly. And it's really hard to do that, to remember how all the memory models work. So that's why you should be drawing it out as you go. Just a warning, because remember that everything inside of that hash map is just a reference to some other object. So what we're going to do is train from text. First of all, you're going to wrap the first 3 words to the end, just to make it easier to predict stuff. And then you're going to train it on words and characters. So you can do either or when you run the program. What I was doing before was with words. So, right, if this is my entire string, then my first prefix is the first degree words. So let's say degree is 3. So my first 3 words is my first prefix, and my first prefix is then I do not. So I insert that into the prediction map. this array list. And of course, that array list is a key and it corresponds to a value, and that value is a word count list. Like this. So we put this prefix in because it doesn't exist in the hash map yet, and that just corresponds to and maps to like 1, because that's what we read. And then we move forward, and now do not like is our prefix, and green is the word. It'll look like this, and it'll go all the way to the end. And so each word we read in is a different prefix. And see how I do not is added to the end again. Normally it was I do not like green eggs and ham. We added I do not to the end. That's to make it easier, because then eggs and ham still map to something. So that's just something you have to do to make it easier. Otherwise there'd be nothing following it, and there'd be nothing to be able to even predict. Now another method you're going to be doing is get flattened list. So we talked about how we're generating these word count list objects. Some of them are complex, some only have one word, right? If first of all degree is 2, and our prefix, our key, is an array list I like, and it maps to word count list dogs, cats, 2 and 3. Well, that's fine, but what get flattened list is it's going to turn this into a list which represents, instead of having a number to represent the count, we'll duplicate it. So if dogs is 2, then we have dogs, dogs. Cats is 3, cats, cats, cats. Dogs, dogs, cats, cats, cats. Why do we have that instead of this? Well, this is useful for like keeping all the information kind of contained inside of a hash map, but then what this straight list is useful for is generating the next word. So given some prefix like I like, we're going to need this flattened list of words, because we're going to choose a random word from here to generate the next word. So again, given a prefix I like, using the Markov model prediction probability stuff that we were talking about earlier, there should be a 3 out of 5 chance of generating cats and a 2 out of 5 chance of generating dogs. And if you just generate a number and choose a random element in this list of 5 words, guess what? 3 out of 5 chance that the random word you get is going to be cats, and 2 out of 5 it's going to be dogs. So that's perfect. So that's why we flattened it, so that we can just choose a random word from one of these 5, and that's our prediction. That's what we predicted, and that represents the statistics of the word count list. So that's perfect. And then we have generate. So generate next, given a prefix finds a prediction word, generate just generates an entire paragraph or sentence or whatever. So first of all, what we're going to start with at the very beginning, if you see here, see how the first 3 words or first 2 words, it's in some cases don't really make sense. Why would the paragraph start with try them? Like, there's no context. It makes no sense. It's the least logical part of this stuff that's generated. That's because we don't have anything to predict with yet. So we don't know what to start with. We don't know what the first 3 words should be. So we'll just choose a random word, even if it doesn't make sense. Like, we'll eat them. That doesn't make sense, but we got to choose something as our first 3 words, or our first degree words. But from there, once we have our first 3 words, we can use them to generate a word, like here. And that's actually used, statistics and whatnot to get a smart word that follows. So remember, we have these 2 methods that we already wrote, generate next, and that uses flattened list. So to generate a word, to generate a prediction given this prefix shouldn't be too hard, because we already have methods that do that. So we generate here, and we add it to our string of all of the words that we've generated so far, to our array list of all the words. It doesn't have to be an array list. You choose how you want to save all the words you generate. It could be a string, whatever, string builder. But anyway, you save the new word, so now you have will eat them here. But is our prefix now will eat them here? No, our prefix is always length 3. So our new prefix is eat them here. It's the last 3 words that we've generated. So eat them here will generate or. So we add or to the list of all the words we've generated, and we make our new prefix them, here, or. And again, remember the memory model talk. Careful how you change your prefix and stuff. Maybe a hint would be using the new keyword just to be safe that you're keeping all the references pointing to different objects. But anyway, your new prefix is going to be them, here, or. And them, here, or will generate some other word, and some other word, and some other word. So eventually you're going to have count words total, and then you'll just return all of the words that you generated. So you see will eat them, here, or. That's the first 5 words we generated, but it's going to keep going. Them, here, or will generate there. Here or there will generate I, or there I will generate do. Right? That's the idea. And eventually it will go all the way to the end till we've reached count. And that's the end result. And that's actually the whole PA. So that's what you're doing is, first of all, all the way here. So first of all, we're training, we're reading, we're seeing what words follow what words in the actual text. And this trains it, and we can do this either with characters or words. The way what I've been showing you is with words, but if you use characters, all that happens is instead of splitting things and reading them word by word, you read each character as its own piece. So this would be like G, R, E, generates another E, or something like that. So this train from text can train either with words or with characters, and that builds up our giant hash map of prefixes and predictions, of prefixes and word count lists, you know? And once we've built that giant thing up, then we can actually use it to generate words, which, you know, we use generate next and flatten list and all that to generate a random prediction given our prefixes. And we know what random words to create because we've already built up this big hash map using train from text. So it's a lot like any AI program. Is first it trains from given data, and then it generates its own stuff, its own predictions. Cool. So that's basically what we're doing. And again, refer to this. This is nice because it actually shows you that there's arrows here, that it's actually references because it's a memory model. So this really important to keep this in mind again, because a lot of people have, you know, null pointers, stuff like that, when they don't take into consideration that everything is a reference. And so again, at the end, it'll do stuff like this. You can run it with some parameters, -d3. Maybe I could say, see how this is different one every time, like them in a box, and then I do it again. Would you like then with a mouse? It's always different because it's random words, but it always sounds a lot like Dr. Seuss. And of course I can do, we give you some other text that you can train on, or you can write your own. You can write your own short ones. See, so we did a different one with the Odyssey, and it generated a bunch of words based on the Odyssey. So what I could even do is say test.txt, and I could say, hello, this is a test of Markov model. It's a very short sentence, so it probably won't look that great, but that's not really the point. The point is I used it, and I see how this always generates a certain amount of words. That's okay. We have the write up here, and jump to this part and you'll see some example stuff here. So for example, I could say -n1000. You can take a look at this. You can see C. I'm using W. That means they're using characters and I'm using words. So if I did this with C, it's a little different, right? I'll go back to W. It's like this, and I'll do N 1000, and it generates a whole like giant essay. Anyway, so you have a bunch of different test options here, and one really useful thing is you can use Y here as input, and of course go to the write-up and look at all the different options you have. You'll be implementing some of this stuff too. So anyway, so Y will actually print out, along with this text, which is the prediction, it will also print out this, which is, let me do this again with, see? So this is basically all of the prefixes and their values, all of the prefixes and what word count list is mapped to them. So here the prefix is more complicated. We have a lot of, not, could not, the, rain, and, you, in the, and sometimes not like them. That's a really common prefix. It maps to a huge word count list of like a bunch of different words. And some of them, could, you, in, is always followed by the same word. And because there's so many ones here, that's why every Green Eggs Ham program always sounds like it's Dr. Seuss's, because there's like very little variety. If I did this on Odyssey, you could see that. It might take a while. If I did this on Odyssey, you will see that eventually, if it prints out, that it's much more complicated, and that there's a lot more common prefixes. And one thing you could also do is make the prefix 2 instead of 3, and that'll change up the probability. So anyway, let's see if this finishes running. The point is, write your own little text files and run them and print out the corresponding hash map and word count list that comes out of it, because it will help you debug and make sure that everything looks the way it's supposed to. Is this ever going to finish? Let's use something else. See, we give you a bunch of these. We have, let's try Turing.txt. It's really slow. So anyway, this will print out like what you saw here. It will print out like memory models. Hey, there it goes. See? So there are a lot of prefixes which only follow one thing, but there's a lot of prefixes because it's a long novel. But yeah. So what I like about Green Eggs and Ham is because he always goes, not eat them in a, and then there's like 5 different words that follow not eat them in a. I would not on a boat. I would not on a moat. So it's like the same prefix followed by a different prediction. Whereas here it's a lot of different prefixes, but always the same prediction. But in some certain prefixes here, because there's so many, they might be followed by like a pretty complicated word list, possibly. But the best text file is Green Eggs and Ham. But anyway, so hopefully this gives you a nice little overview of what we're doing here. Hopefully that kind of makes more sense with why we're using hash maps and word count lists and how probability and all that comes into play. But that's it. So again, we'll have tutor hours, ask on Piazza if you have any questions, and good luck on Markov language model. Thanks for watching.